Hello, hello, hello.
Nice.
Hello, Haripriya. Acha, the last class, today we'll be completing this one. Did you remember the last one? The last class concepts. Work done is splitting a big drop of radius r into n smaller drop. I have asked you to calculate the work done in combining n small drops of radius r into one big drop.
No, sir, I didn't. Questions, sir.
Actually, it will be same. The things are there are n small drops. Radius r is there. First, you need to calculate the total radius r of the big drop that is going to form. So n into 4 by 3 pi small r cube is equal to 4 by 3 pi into capital R cube will be there. So you will get a relation n into r cube is equal to capital R cube. So capital R will be equal to n power 1 by 3 into small r. That's one relation. Now what will be the work done? Work done is surface tension into change in area n into 4 pi small r square minus 4 pi capital R square n power 2 by 3 into small r square. You can take actually r power n power 2 by 3 common, you can take 4 pi capital T n power 2 by 3 into n power 1 by 3 into r square minus r square also I'll take common.
Yes, sir.
That thing you should remember. So did I give question on this? No, I did not give you. Did I discuss the pressure difference? Not yet. Okay. Achha, let me give you the question then. One question I'll give you. Then we'll discuss the capillary rise and fall and the pressure difference in the soap bubble and the liquid bubble. Hmm. Achha, tell me after this, what should I start? Should I start thermodynamics or should I start this one, heat and mass transfer?
Anything else?
What device saying? Thermodynamics.
Yes, sir.
Okay, thermodynamics. Anything is okay. Haripriya, thermodynamics device saying thermodynamics will start. You remember now? Surface energy is nothing but the work done. Work energies are same. Try this. If you're not able to solve, I'll solve it. Or let me solve it simultaneously. You solve by yourself. If you're not able to understand, look at my solution. Two small drops of mercury each of radius Kepler. Will solve slowly.
Sir, option
Option A. No, they're saying it is option B. I'm also getting option B only. You calculated final ratio of final surface energy by initial surface energy, I think.
Yes, sir.
Silly mistake. But they have asked initial total ratio of total initial surface energy to the final surface energy before and after the change. Kanishka, okay na?
Yes, sir. Sir, can you hear me?
Yes, I can hear you.
Okay.
Okay na, this question, this you are able to solve, understand? You understood this
Yes,
one?
sir.
Okay, very good.
Yes.
So for everyone it is clear. This is how you calculate the surface energy and the work done when bubbles are combining or these things are combining. Now we'll discuss the next concept, that is excess pressure. Today I'll try to complete it. Excess pressure inside a bubble. Actually this chapter got extended because of my health. I was not able to take classes now. Otherwise we would have started already new chapter. Excess pressure inside a bubble. There are two types of bubble. One is a liquid bubble and one is a soap bubble. The only difference between the soap bubble and the liquid bubble is in the soap bubble there are two surfaces. You will be able to observe it properly when you see one soap bubble. Now there is a toy that throws bubbles, soap bubbles for children's. When you will be able to see those bubbles now, if you look carefully, the upper surface will be it appears that the upper surface is moving related to the lower surface. So that means the soap bubble has two surfaces. So while calculating the forces, surface tension has to be multiplied with two surface areas. That's the only difference. Now, how do we calculate the pressure difference? Let me show for the liquid bubble. Then you will be able to understand. Actually, the derivation is not important, but I'm telling you, if at all they change something, you will be able to do the questions then. What's the case? This is a liquid bubble. The shape did not come. Ready? Now what's there? We need to find out. Suppose the pressure inside this bubble is Pi. Pressure outside this bubble is P naught. We need to calculate this difference. Obviously, the Pi will be greater than P naught. That's why the bubble is of this shape. But we need to find out the difference, Pi minus P naught, what it is. How do we do it? We take the help of surface tension. I'll make a section. You believe this is a section drawn in such a way that it's showing the cross section of this bubble. Now, okay, it is showing the cross section of the bubble. Now, if you see, suppose the radius of this bubble is small r. If I take any random region, any random point, inside pressure is Pi, outside pressure is P naught. So the force on this particular small area that's present here will be what? Pi minus P naught into the small area, delta A, the area of this, correct? Now for this force, what I can do, I can take two components. One will be the horizontal one, other will be the vertical one, right? The vertical similar component, if I have taken the bottom, that also will have the vertical component and the horizontal component. If you see, these two areas are symmetric and exactly same. The vertical component will be actually cancelling out. So the only component that we actually care about is this horizontal one. This horizontal component only we care about. And this horizontal component, since it is a pressure, the effective area on which this horizontal pressure, effective area which will be giving rise to the force, horizontal force, will be this cross-sectional area because it is perpendicular to the horizontal force. So the pressure Pi minus P naught multiplied with this cross-section area will give us the net horizontal force. Clear? On the right half, we are taking only one half. Now this force is actually balanced by what? It's actually balanced by the net force acting towards the left because of the surface tension. What is that? T into 2 pi r, circumference, surface tension. So if we equate them, we'll get Pi minus P naught is equal to 2T by R. This is the pressure difference in a liquid bubble. Understood? Actually, this is a derivation, but still I am saying this derivation part is not important. The only result is important. You should remember this result only. Diva, okay na? Hare? Haripriya, okay? Kanishka, okay?
Sir, for a bubble, it shouldn't be there two surfaces.
For liquid bubble, there are one surface. For soap bubble, there are two surfaces.
Okay.
Why? You can observe yourself. In liquid bubble, if you see, na, you won't be able to, actually, you won't be able to see liquid bubble that easily because you won't find the bubble. Only when it is popping out, you will be able to see the bubble. But in the case of soap, you will be able to see the bubble properly. And the soap bubble, in the soap bubble, it appears that the bubble is like this and upper surface is moving so that you will be able to see the interference of colors. Upper surface tends to move with respect to the lower one. Rest all things you understood, na? Derivation, everything. Okay, everyone understood. Now coming to the soap bubble, the only difference with the soap bubble is it has two surfaces. So the effects, which will be Pi minus P naught into pi r square, will be equal to, there will be surface tension acting on two surfaces. So T into 4 pi r. The two circumference will be counting for surface tension because two surfaces are there. So pi will cancel, r will cancel. So we'll get Pi minus P naught is equal to 4T by R. These two results you should remember because they will be actually useful for you. Actually, there was a question actually I wanted to give you. Acha, I'm going to give you one question. Just try to understand this question and then tell me, are you able to understand and how are you able to understand how to solve this one or not? First tell me, are you able to understand what they're saying? Or if you want me to make you understand, then tell me. First try to understand by yourself. Tell me, Diva, able to understand this one? Or you want me to explain?
Yes, sir, I'm trying.
Okay, right. Any one of you, Kanishka, Diva is trying, Kanishka or Haripriya, if you are not able to understand, I'll explain you. If you are able to understand, try to do it.
Actually, is the answer 1.3?
No. The answer is 4. Do you want to know how? See, the situation is there are two soap bubbles of radius 2 and 4 centimeter. Here R1 is equal to 2 and R2 is equal to 4. The radius of curvature of common surface in centimeter, when they come to contact, what will be the radius of the common surface they are asking? No, when they were individual, you can write the relations like this. P1 minus P0 is equal to 2T by R1. P2 minus P0 is equal to 2T by R2. When they have come in contact, the radius has changed. Radius of the combined surface has changed, so we can write P1 minus P2 is equal to 2T by capital R. Now solve these three equations and get the answer. If you do 1 minus 2, you'll get P1 minus P2 is equal to 2T into 1 by R1 minus 1 by R2. But P1 minus P2 is 2T by R. So 2T by R is equal to 2T R2 minus R1 by R1 R2. 2T 2T get cancelled. So R is equal to R1 R2 by R2 minus R1. This is actually a derivation. Using they give this formula as the final result, and they expect you to use this formula directly. But I don't think this should be a part of derivation. This should be taught to you. You should be able to figure out by yourself. It's not difficult. So that R will be 2 into 4 by 4 minus 2. 4. Answer 4. Tell me, able to understand?
Yes, sir.
What about you, Haripriya, Kanishka?
Got it, sir.
Yes, sir.
Actually, at first go, it's not easy to understand this one, that we'll be solving like this, because usually you don't get the approach. But this is a kind of question which they give repeatedly. Rest all are easy. Now let me teach you the next concept, which is capillary rise and fall. Did you ever observe it's easy to drink something like some soft drinks or something you are drinking, or juice or anything you are drinking, you tend to use a straw, or the coconut water. Coconut water, it's very difficult to drink like this. It will spill out. And it's easy to drink if you put straw in it. Usually putting the straw and then drinking it, it's easy. Many people will think just because we are sucking it, it comes up. There is a combined force. Once you are sucking it, it's coming towards you. Other thing is, because of the capillary action, automatically the water level rises up in the capillary tube. Why? That's what we are going to understand. Actually, things are very, the nature is very, it's actually good. The things which are beneficial to us, which we can drink, they have the tendency to come towards us, which are good for us, which are okay for us. And the things which are actually poisonous to us, they have the natural tendency to go away from us, so that the equilibrium is maintained. I'll tell you why this happens. In the case of straw, it's not that whatever liquid we put in the straw, it will naturally come up. This mercury, which is poisonous to us, it won't come up, it goes down. So it is difficult to suck the mercury up. It only happens with water and certain liquids whose angle of contact is less than 90. Now, I need to tell you what is angle of contact. You need to understand what is angle of contact. If this is surface, water, how it spreads. If you drop a water droplet, if you drop it, water droplet will try to spread. Why? Because its angle of contact, this is the surface of water. This is the angle of contact. The less is the angle of contact, more easily the liquid spreads. Now, talking about the mercury, I don't know whether you have seen mercury falling down or not. Mercury actually tends to maintain its spherical shape. It turns into very small bubbles when it falls down. And why it happens? Because this mercury has the angle of contact which is greater than 90 degree. It's like this. This is the surface. This is its angle of contact. And this theta is actually greater than 90 degree. Mercury. That's why, because its angle of contact with water, with the surface, is greater than 90 degree, that's why it tends to go like this. Means it tries to form the bubble. So it may divide into very small pieces, but every piece tries to maintain the spherical shape. Again, I am repeating, the angle of contact is the angle which the surface of the liquid makes with the surface of contact. This is the liquid surface, the pink one. It's making the angle with the surface. So this is the angle. This is the angle of contact. This in case of water. Now, in the case of mercury, this is the surface. It's making an angle of theta which is greater than 90. Okay. So it tries to, because this angle is greater than 90 degree, it tries to maintain the spherical shape. If it was less than 90, like the above one, it will try to spread out. Clear? Now talking about the water, this is water. If you look closely, its surface will be like this. This is the surface tension acting like this surface. This is vertical. This is the angle of contact theta. So I can actually take the component of surface tension in both the directions. One is this T cos theta like this, and the other component will be T sin theta. And if you look carefully, T sin theta component will be cancelling because it is equal and opposite. So the only tension component which is responsible for making it remain up is T cos theta. So the force due to surface tension will be T cos theta into 2 pi r, where r is the radius of this curvature. Clear? Now this pressure, let's say the pressure here is P1, pressure above is P2. Actually it should be P0. Atmospheric pressure. Obviously, if the curvature is like this, P0 should be higher than P1. Clear? Also, this surface is also open to atmosphere. So here also atmospheric pressure should be P0. Pressure should be P0, like the upper surface of the curvature. But below, the pressure will be P1. If it has risen by height h, if it rose by height h, we can just relate this pressure P1 and P0 like this. P1 plus rho gh will be equal to P0, because pressure on this surface, this horizontal surface, should be same. We are moving from P1 plus rho gh should be equal to P0. Okay. Now on the upper surface of the curvature is P0 atmospheric pressure, bottom surface is P1. So we have got a relation between P0 and P1. But if we try to look at the force here, which is trying to maintain equilibrium with T cos theta force, surface tension force, that will be P0 minus P1 into pi r square. Clear? Understood this part?
Yes, sir.
Okay, try to cancel this r, and this one. So T cos theta, 2T cos theta by r is equal to P0 minus P1, which is rho gh. So I can get a relation. H is equal to 2T cos theta by rho g r. This is the relation which says how much height the liquid will rise in a capillary. And why it is rising up? The reason why it is rising up, because the angle of contact of the liquid is less than 90, like this. If it was like this, it has to move down, because pressure difference on the upside will be more than the pressure difference, no, pressure on the up here in this case, when the curvature is like this, the pressure on the top portion should be higher than the pressure just below the curvature, and that is why it has to rise up. Otherwise, if I made the reverse relation P naught plus rho gh is equal to P1, that won't fit here. The result will be negative. Understood why it rises up? Now the same case if I draw for the mercury, how it will happen? See, the result will be same, but the things are different. In the case of mercury, what happens? It goes down. The mercury goes down in capillary also. Here. Here will be the pressure P naught, and here will be pressure. What is happening? Here will be pressure P1 now, and in this case P1 should be greater than P naught. T cos theta will act downwards because this will be angle theta in this case. Now T cos theta into 2 pi r, the force is downwards. This will be balanced by P1 minus P naught into pi r square. Now in this case P1 should be greater than P naught because this is curved like this, and for this to maintain, the pressure P1 should be higher than P naught, because here the pressure will be P naught plus rho gh should be equal to P1. In the above case, P1 was lower than P naught. It can only happen if the liquid falls down. Same calculation, result will be same. But this can only happen when the liquid is going down. Mercury is for the means what we say, calculation will be actually same. The answer will be actually same. That is H is equal to 2t cos theta by rho gr you'll get. But the thing that you need to understand is liquid with the angle of contact which are greater than 90 degree tends to fall down by height h in the capillary, and the liquid with angle of contact less than 90 tend to rise up. Water is one of them. Understood? By this, I think your chapter is over. Now let me give you some question. Achha, can you solve this question? It's not based on this capillary rise and fall, but this is a different one. You understood the concept, no? Capillary rise and fall. How to calculate the height? Formula will be same, but the concept is different. Why it falls and why it rises. Try to solve this question. So I can draw the diagram also. I can show you the diagram also here. In this case, you have to take into account both the mg as well as the buoyancy force also. Are you getting idea how to solve it? Let me solve it. Only 2 minutes are left. T. Here, what forces will be acting? One will be mg. One will be buoyancy force. Here in this case, 0.2 g. It's 200 gram, no? It's a cube. So 10 centimeter. So cube of length A 10 centimeter. I can write it as 0.1 meter. The
So
volume
you
will,
do not need to convert it into meters. Everything is given in
but,
CGS.
but
You
0.
can convert it into lambs.
gram, na?
They've given it in CGS.
Okay. But the equation that I'll frame is torque. I'll take the torque about O. FB minus, sorry, mg minus FB. mg minus FB into 2 should be equal to 0.2 g into 25. But this 0.2 is in kg, na? What they're asking? Unknown mass. Actually, okay. Acha, unknown mass they're asking. But the FB is there, na? Rho GH, rho G into V rho G. You will have to convert. Half of the volume is inside, so it will be A cube by 2 into rho water into G. M minus A cube rho water by 2 into G into 2 is equal to 0.2 into, if I convert it into grams, actually I think I have to convert it, Haripriya, because things are changing here. It is 0.2 kg, na? This kg has to be converted in grams, or otherwise I will have to take A in terms of this one, say meters. This GG will cancel. 2 into 25, 5 by 2. This will be 5 by 2. And M minus, this is 1000 into 10 power minus 3 by 2. Okay. M minus 1 by 2 is equal to 5 by 2. M is 3 kg. Now okay. This is the answer. Solved. What I was saying, na, Haripriya? G, this is in centimeter, no need to convert. This is also in centimeter, no need to convert. They will cancel out. This 0.2 is in kg, because this is in kg, GG got cancelled. This is in kg, so I have to convert this inside A, the A which is there, na, is inside A in meters. And also raw water that I am taking should be in kg per meter cube. That's why I have taken raw water as 1000 and A as 0.1 meter. Understood? Otherwise things will go wrong. Okay, this is solved. So this topic is over. In the next class I'll start, or if you will ask me, I'll give you some more question to practice. Otherwise we'll start thermodynamics, new topic. Let's end the class then.
Thank you, sir. Bye, sir.
Bye bye.